In chapter 5, we continue our work in functions, and we're going to talk about two specific types of functions in chapter 5, polynomial functions, which are in section 5.1, 5.2, 5.6, 5.7. So we'll do those four sections first, and then we'll backtrack and do rational functions, which are in section 5.3, 5.4, and 5.5. So it's a little bit of a jog around, but don't worry, the deadlines are set, just follow those deadlines. In section 5.1, we start with our introduction into polynomial functions. So in part 1, what you're going to see on the handout, first of all, is some data about major hurricane strikes. And it talks about in 2005, Hurricane Katrina struck the Gulf Coast, killing 1,289 people and causing an estimated $200 billion in damages. The following data represents the number of major hurricane strikes in the US, each decade starting in 1921 to 2000. So what you see is a data table, the decade and the number of hurricane strikes. And what you then also see is a beautiful graph. And the graph shows on the horizontal axis, the decade since 1920. So this is time, basically. And on the vertical axis is the number of hurricane strikes. And again, those are major hurricane strikes, not minor hurricanes, if there is such a thing, but there is. So what you're going to see is a beautiful picture that looks something like this. Again, it's on the handout so you can see it. What we're after is the fact is that this graph and this example represents something called a polynomial function. So the graphs of polynomial functions are both smooth and continuous. Now, smooth means that there are no sharp corners. If you think about our graph of the absolute value function, we know that that graph looks like this, and it has that nice, beautiful V shape to it. That's going to be considered to be a sharp corner. We will not see those. No sharp corners in a graph of a polynomial function. Additionally, it's continuous. Continuous simply means that you can come in and trace it without lifting your pencil, or I like to say it, you can walk along it without falling or jumping. So what we're looking at are the polynomial functions. So what are polynomial functions? Let's consider two that we've already looked at. So we've already looked at some polynomial functions. We didn't really call them that, but they are. So we have linear functions. And those would be functions of the form f of x is equal to mx plus b. Those are lines, and we know what those are, so we've seen those. F of x is equal to 3x minus 2. F of x is equal to 2/3 x. Let's make that a negative 2/3 x. And then also don't forget g of x is equal to 2x, or finally, h of x is equal to 5. So those are all lines that you should be able to graph, right? A positive slope, a negative slope, a positive slope through the origin, and a horizontal line. They all fit this definition of smooth and continuous. What else have we dealt with? Sorry, the eraser fell onto the floor again. Just keep knocking it off. We've also already seen quadratic functions. So with a quadratic function, which we talked about in the previous chapter, chapter 4, we know those are graphs of parabolas. And if you think about the graph of a parabola, sure enough, it is smooth and continuous. So that would be something like ax squared plus bx plus c. That would be the standard form. The ones that we've looked at are x squared plus 2x plus 3. Maybe f of x is equal to 4x squared minus 1. You could also have g of x is equal to negative 3x squared minus 2x. So those are all examples of quadratic functions that would all graph as parabolas, which are smooth and continuous. So that leads us to a general definition of a polynomial function. Now this is probably the most math-ish formula that we will ever write in our class. But it's important that you look at it and then recognize what we're dealing with. So on the handout, as you see, a polynomial function is defined as f of x is equal to a sub n x to the n power plus a sub minus 1 times x to the n minus 1 power plus dot, 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 all the way down to a sub 1 x plus b naught. So a couple of things to notice about these. First of all, the a's are the coefficients. They can be any number as long as they are real numbers. So they could be fractions, they could be decimals, they could be square roots even, but as long as they are real, so they won't see i's, so no i's floating around in those coefficients. The other thing to notice, the exponents on the variables are all whole numbers. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, no negative exponents floating around, no fractional exponents floating around. And that's what makes a polynomial function, basically. This is what makes a polynomial function, I guess would be the way to say that. A sub n is going to be the leading coefficient. It is the coefficient on the highest power of x. The degree of the polynomial function is the highest power of x that appears in the polynomial. The degree of this polynomial would be degree n. And we'll do some practice here in just a minute. So this would be an nth degree polynomial. It's written in standard form. So standard form means that you see the decreasing order of the exponents. An example of standard form on your handout. So standard form would be something like f of x is equal to 3x to the fourth minus 2x cubed plus x squared minus 5. So that's in standard form. Again, notice the things that we're talking about. The leading coefficient is 3. The leading term is 3x to the fourth. Notice that the exponents are counting down. It's okay if you don't have every single exponent starting at 4 all the way to 0, but they do need to count down to be in standard form. Notice those exponents are whole numbers, right? No fractional exponents, no negative exponents. You will also have factored form, and we'll need both of these forms for future work. So factored form of the polynomial, of a polynomial, would be when it's written as a product of factors. So something like 2x squared times x minus 1 times x plus 3 to the 4th. So it's already been factored for us and broken down. So depending on what we need to do with the polynomial is which form is the best form for what we're working with. But it is important to recognize that they are two distinctly different forms. Here it's written as a product of factors. Here it is all expanded out. Okay, so let's do an example. And what we're going to work on is making sure that the vocabulary we're using is making sense to you and that you're learning that vocabulary, because this whole section is a lot of new terms and different concepts from what we've been dealing with, but they tie in nicely. So example 1 gives us 4 different functions and asks us, first of all, determine which are polynomials. If it is, state its degree, identify the leading term and the constant term. For those that are not, tell why they're not a polynomial function. So example A says f of x is equal to 2x to the third minus 7/3 x minus 1. So the question is this a polynomial? Well, the answer is yes. It fits our definition of a polynomial. So in other words, the coefficients are real numbers, which they are. So 7/3 is still a real number, right? It's a fraction, but it's a real number. And the exponents are whole numbers. So it's a polynomial, so yes. And then what do they want us to do is state the degree. So the degree is, when it's in its expanded form, the largest or highest exponent we see, which is a 3. So this is a 3rd degree polynomial. And they want to know the leading term. So the leading term is the one that which has the highest degree. For us, it's 2x cubed. And then the constant is the term that has no x on it. In this case, the constant is a -1. Now, if that -1 weren't here, it would not have a constant term. So the constant term is the x to the 0 power. Or B says, okay, what if g of x is equal to 3? So believe it or not, this is again a polynomial. It's our definition, right? So in terms of our definition, the coefficients are real numbers, because 3 is a real number, and the exponents are whole numbers. Well, the exponent here is at x to the 0 power, and 0 is a whole number. So we're going to say yes. It is a degree 0 polynomial. It's a 0th degree polynomial, and that's because there's an invisible x to the 0 power sitting right there. So the leading term is the only term, which is 3, which also happens to be the constant. So the constant is also that 3. So think about this. Isn't this a horizontal line at 3? So sure enough, it's smooth and continuous. Okay, C says h of x is equal to 3x to the 1/2 minus 7. This one is not a polynomial. And the reason it's not a polynomial is because it has a fractional exponent. So that exponent is not a whole number. Not a whole number. And that's the reason why it's not a polynomial function. It's that 1/2. Example D says, okay, what if f of x is equal to 3x minus 5 plus 1/2x? So what do you think? This one's also not a polynomial. A little more hidden on this one. So this x in the denominator is the issue. If we were to rewrite that, I'm going to keep the 1/2 the way it is. 2, I'm not going to move. But I can bring that x up and write it as a -1. And -1 is not a whole number. So more importantly, you have an x in the denominator. Now, this is a rational function, which we'll talk about eventually. But for now, it is definitely not a polynomial function. I hope that helps solidify some of those vocabulary terms. One more example in this part of the section. So the next example, this is example 2. It wants us to determine the degree of the polynomial function and state whether the function is written in standard form or factored form. So for A, I'm going to rewrite it because, believe it or not, it's not in either form. So I'm going to rewrite this as 7x cubed plus 5x plus 9. Now, the original handout, you'll see the 5x is written first, but I need it in this form. So it is in standard form, and I know that because it's been multiplied out. I don't see those sets of parentheses implying multiplication. So it's in standard form, but what's its degree? Well, the degree, degree is the highest power we see, and the highest power we see is a 3. So this is a 3rd degree polynomial. And in the back of your mind, you should be thinking about the other polynomials we've already dealt with. So all the quadratics were 2nd degree polynomials because they were x squareds. All of our linear functions would have been a 1st degree polynomial because they just had x to the 1st power. So in the back of your mind, that should make some sense because we've already been dealing with it. B says q of x is equal to 3 times x minus 1 times x squared plus 1. So there's our polynomial. This one's in factored form. You know that because you see those parentheses. So it is in factored form. What about its degree? Well, to get its degree, I would need to expand it. I will never have you expand it, but we can pretend to expand it and take a look at what the x would give us. So if we multiply this x times this x squared, we're going to get the largest value of x we could get, and that would be an x times an x squared is an x cubed. So this is also a 3rd degree polynomial. The 3 out in front would be the leading coefficient. And C says q of x is equal to 7 times x minus 1 to the 3rd power times x plus 5. So 7 times x minus 1 to the 3rd power times x plus 5. This is in factored form again. You know that because you see all those parentheses sitting in there. And now we're going to come in and multiply it out or think about expanding it. So this would give me an x to the 3rd. So x minus 1 times x minus 1 times x minus 1 gives me an x to the 3rd. But I have to multiply it by the other x that's sitting there. So that would be x to the 3rd times x gives me an x to the 4th. So it's a degree, or it's a 4th degree polynomial. Its leading coefficient would be that 7 if you were to expand it or multiply it all out.